In this question, we will be studying free body diagram, resultant force, equilibrium of rigid bodies, and the concept of turning effects of forces. Let's take a look at this question. One of the late Michael Jackson's famous dance moves was the seemingly physics-defying 45 degrees leaning dance move, where he leaned his body forward at 45 degrees to the ground and remained in equilibrium in that position for a few seconds without falling forward as shown in figure 3.1. In fact, the dance was only made possible due to specially made shoes which were hinged to the floor, preventing Michael from falling forward onto the ground. So that solves the mystery of how he did this physics-defying leaning dance move. Let's look at the free body diagram. Figure 3.2 shows the force F acting on the body by the hitching mechanism, which is 20 degrees from the vertical, and the position of the center of gravity, CG, which is 120 cm from the tip of the shoe. The horizontal distance between the tip of the shoe to the hitching mechanism is 15 cm. Part A of the question asks for the two conditions necessary for a body to be in equilibrium. So what are the two conditions necessary for the body to be in equilibrium? The first condition is the resultant force is 0. So let's write it down. First condition, the resultant force acting on the body is 0. This means that there's no net force acting on the body. The total force acting on the body will sum up to be 0. In other words, all the forces are balanced. That is the first condition. The second condition is the resultant torque or moment about any pivot is 0. The resultant torque, sometimes we call that moment, about any pivot is 0. What does this mean? This means that the sum of the anti-clockwise moment is equal to the sum of the clockwise moment about any pivot taken on the body. So these two conditions are necessary for a body to be in equilibrium. Take note what is meant by equilibrium. Equilibrium in layman term means that it is stationary at rest. It is not moving, it is not rotating. So this is what is meant by equilibrium. Let's take a look at the next part of the question. Taking the tip of the shoe to be the pivot and the weight of Michael to be 570 Newton, calculate the force F when Michael was doing the 45 degrees leading dance move. Now how should we proceed to solve this question? Let's look for hints given in the question. Well, one obvious hint is take the tip of the shoe to be the pivot. This means that we will have to use the principle of moments to solve this question. First of all, to make this solving a question easier for us, we should draw the free body diagram acting on Michael. So, it is given that his weight is 570 Newton. So let's draw the weight of Michael, right? Indicated by this blue arrow here, W. Next, there's this normal contact force. Now we have to draw the normal contact force at the tip of the shoe because that's the only point he's in contact with the ground. And it has to be slanting. This normal contact force is not vertical. Why? Because if you look at the force F, it is slanting at an angle 20 degrees downwards. So more or less, our normal contact force should be inclining to the right from the tip of your shoe. So say somewhere like this. And that's called the normal contact force N. So these are the three forces that are acting on Michael. Now, if we are taking the tip of the shoe to be the pivot, then there's one conclusion we can make is there is no moment for force N about the pivot. Why? Because this force acts on the pivot itself. There is no perpendicular distance for force N. Thus, zero moment for force N. Therefore, there are only two forces that are left to calculate the moment. So one of it is the weight of Michael. The other one is force F. So let's proceed to calculate the perpendicular distance for each force. Now how am I going to calculate the perpendicular distance of the weight W? Let me draw the line of action of the weight W. And the distance is actually from the tip of the shoe to the line of action. So this distance, let's call it D. Now how am I going to find the value of D? Let me draw a triangle. Alright. Well, the hypotenuse represents the slant of Michael. And this distance, okay, from the tip of the shoe to the CG is 120 cm. Now the angle is slanted 45 degrees, and this is D, which is what we need to find. So using a simple trigo function, we can find that D is 120 cosine 45 degrees. So the perpendicular distance of W is found. Next, we need to proceed to find the perpendicular distance of force F about the pivot at the tip of the shoe. Now to do that, it is better for us to resolve force F into the horizontal and vertical direction. So let me resolve the force F horizontally and vertically. Now recalling how we resolve forces, the horizontal component of force F will be F sine 20 degrees, whereas the vertical component will be F cosine 20 degrees. And after resolving the forces, it is very clear that F cosine 20 degrees, which is the vertical component, is perpendicular to the distance of 15 cm. So I hope you can see it's this distance. What you can see is perpendicular to the 15 cm. So with all these distances found, we can proceed to calculate force F. Now you may wonder what happens to F sine 20 degrees. Well, that force is parallel to the distance of 15 cm. Therefore, F sine 20 degrees does not contribute to the moment. Perhaps I should write it down. Right? The horizontal component has no moment because it is parallel to the distance. of 15 cm. Remember, moment is calculated by multiplying the force and its perpendicular distance from the pivot. Next, we need to decide which is the clockwise moment, which is the anti-clockwise moment. Now, W creates the clockwise moment about the pivot, while the force F creates an anti-clockwise moment about the pivot. So, from the principle of moments, the clockwise moment is equal to the anti-clockwise moment about the pivot. This principle is only true when the body is in equilibrium. So the clockwise moment is W times D. The anti-clockwise moment is F cosine 20 degrees times 15. Alright, then W is 570 times D, which is 120 cosine 45 degrees, which is equal to F cosine 20 times 15. So doing a simple calculation, F will be equal to 3,431 newtons. Let's proceed to the second and final part of this question. Determine the magnitude of the force acting on the tip of the shoe by the ground. To solve this problem, we need to draw the free body diagram of Michael. Now, this question actually asks for the normal contact force, which we have already identified in the previous question. But nevertheless, we shall redraw the free body diagram. Now, the weight of Michael, is represented by the weight, which acts vertically downwards. His normal contact force, acting at the tip of the shoe, slanting to the right, and is represented by N. And of course, the force F, acting on his body by the hitching mechanism. Next, we shall proceed to resolve the forces of N and F. So, resolving N, the contact force, horizontally, and this horizontal component, I'll call it Nx, and the vertical component, I'll call this Ny. Now, previously we already resolved force F into the horizontal and vertical direction, but nevertheless we shall redo it again. So this is the vertical component of force F. I'm going to call it Fy, and the horizontal component, call it Fx. So after the resolution of forces, we can proceed to use the first condition of equilibrium, which is all the forces must add up to be zero. Hence, vertically, all the vertical components must add up to be zero. There are three vertical forces in the free body diagram. Now, Ny is in the upward direction, so it is a positive force in the vertical direction. The next force we're going to add is the vertical component of F, which is Fy, but it is acting downwards. So it's in the downward direction, therefore it's a minus Fy. Same thing for the weight W, since it's acting downwards. So it's in the negative direction, W equal to 0. Therefore, the vertical component of the contact force N will be equal to Fy plus W. And we know Fy is F cosine 20 plus the weight, which is 570 Newton. And from the previous part, we have already found that F is 3,431. So cosine 20 degrees plus 570. So the vertical component of the contact force will add up to be 3,794 Newton. This is only one component of the contact force N. We have to proceed to find the horizontal component. So similarly, horizontally, all the horizontal forces must add up to be 0. There are only two horizontal components. So nx, which is in the positive x direction, plus fy, which is in the negative direction. I'm sorry, it should be fx in the negative direction equal to 0. So nx is simply equal to fx, which is f sine 20. And we know that the force F is 3,431. So 3,431 cos sine 20. And so horizontally, all the forces will also have to add up to be 0. So all the horizontal forces adds up to be 0. Now there are only two horizontal components, which is nx in the positive x direction plus fx in the negative x direction. Both adds up to be 0. So the horizontal component of the contact force is actually equal to the horizontal component of force F. And that horizontal component, force F, is F sine 20, which is 3,431 sine 20 degrees. And the answer will be equal to 1,173 Newton. Well, we have not finished yet, because the question asks for the magnitude of the force. We only found the two components. So we have to combine these two components using Pythagoras theorem. Let's start on a new page. So the horizontal component of the contact force was found to be 1173 Newton, whereas the vertical component was found to be 3,794 Newton. So we have to add them up as stated previously using the Pythagoras theorem. So 1173 squared plus 3794 squared, putting square root. And the answer is found to be 3971 Newton. Now the question only asks for the magnitude of the force, so the direction is not required. But if you're asked to find the direction of this contact force, then you need to find one more variable, which is the angle. So let's indicate the angle here, theta. The angle, the contact force, is inclined to the horizontal. So since we already found the two components, nx and ny, tangent theta is simply ny over nx. Therefore, theta is the inverse tangent of this ratio ny versus nx. So this is just an extra piece of information given to you in case you're asked for the direction of this contact force. Well, that's it for this question, and I hope this question has enhanced your understanding of forces and torque. Thank you.